and welcome to this week's episode of Follow Researcher. Last time I introduced you to the concept of system-focused research and gave some examples of how I've carried out system-focused research throughout various projects in Alaska, Iceland, Washington State, and Antarctica. This week, we're going to be talking about systems and system models in the context of my master's thesis research around Antarctica. A systems approach to science is a way of thinking about a problem within a broader context of its environment and the things within its environment. To more thoroughly introduce the concept of systems and system models, I'm going to give you an example of how an impact on one resource on my farm growing up had effects that reached beyond just that one resource. Hay is a feed resource for the animals that we had growing up on my farm, mostly cows. And in order to store it for the winter, for feeding our animals throughout the winter, in the summer it has to be cut and have time to fully dry before we harvest it. Otherwise it can mold or greatly degrade the quality of the hay. When I was a kid, we had some really rainy summers where we would cut hay and there just wasn't enough time for it to dry to have us harvest it before it was rained on. And that meant that our hay crop lost value and was not able to be used to feed the animals in the winter. So we would have to buy much more expensive hay. This then impacted my family. We can break systems down into smaller components to make them easier to study. This is almost like drawing an imaginary boundary around the part that we want to investigate. Our system boundary, in this scenario, is considered the farm. The farm involves the crops, animals, and income that are related to it. And it was impacted by another system, or weather and climate. The Earth is a really complex system, and it would be nearly impossible to understand everything going on at once. I study icebergs to understand what the conditions are like within the ocean, using satellite imagery or pictures of the Earth taken from space to see how elevations of icebergs are changing over time. And then I investigate to see what that says about other aspects of the physical system. As in any model, we need to define system bounds. The system boundaries of my iceberg melt model include the iceberg and the water immediately around it. We can also make a conceptual model of the entire glacier and ocean system, where we consider the interactions that occur between the ocean, air, and glaciers themselves. It is in considering how changes in one part of a system affects or leads to changes in another part of the system that we can get a more detailed understanding of how everything on our planet is linked. For example, iceberg melt can tell us something about the conditions in the ocean. The conditions in the ocean affect the glaciers that end in the ocean. And if there's more melt in glaciers, that can lead to more freshwater input back into the oceans. This freshwater has impacts on life in the oceans and can also affect humans that live around coastal areas as well. Physically speaking, we know that icebergs melt primarily because of the water temperature in an area and the speed and direction, or velocity of the water, flowing around it. This is because the speed of the water can cause turbulence, which mixes water of different temperatures around the iceberg, melting that. If an iceberg is melting very quickly, we know that water temperatures or velocities have to be high relative to another iceberg that's melting at a much slower pace. This information is important because, 1, Antarctica is very far away and hard to get to, so taking direct measurements of ocean temperature and velocity over a large space is really difficult to do. And 2, glaciers that flow from on land and into the ocean, called marine terminating glaciers, that melt can lead to rises in sea level. So, if water temperatures and/or velocities increase, this can lead to faster melting of ice and more sea level rise at a faster pace. If we can somehow measure the pace at which icebergs are melting in a lot of places all at once from far away, we can understand what conditions are like in the ocean. And this is what I do. Models of a system can range in detail from lists and simple sketches to complex computer simulations. Here, I've made a list of models representing iceberg melt that range in complexity. Each of these has value depending on the purpose and the goals for its use. During different stages of my research, I use sketches, Time 1, Time 2, satellite image series, maps, images that show changes in elevation, graphical representation of processes occurring within a system, mathematical equations representing Earth system processes, and computer models. One important thing to note about using models is that no model is perfect. In our case, we have to make some assumptions about what the iceberg looks like below the surface because we can't see it. So we assume that it has an idealized geometry, or the shape of a cylinder. This is an example of where we use what we know about Earth systems, and we have to make an estimate based on these idealized conditions. Using idealized conditions can introduce uncertainty into our calculations. For example, the below water surface area of an iceberg is likely much more complex than a cylinder, but using this condition, we can calculate things to the best of our ability with the information that we can access. In this case, we can calculate overall iceberg volume. We can think about how I quantify iceberg melt with satellite imagery as an iceberg melt model. I use satellite imagery to calculate the elevation of the iceberg surface. We also know a lot about how ice floats in water due to repeated observations and physical modeling of such a system. These two pieces of information can be used to determine what the volume of an iceberg in two different time periods is and how it has changed over time. Thanks so much for joining me in learning about systems and system models. Next week, I'm going to be talking about patterns of cause and effect in my research. Some questions for you this week include, which other researchers who have done the Follower Researcher program in the past have investigated a system or a key aspect of a larger system? And what was it? Why is it important to review problems from a systems perspective? And what are some examples of problems that would benefit from attempting to answer them using a systems approach or interdisciplinary methods? Thanks so much for joining us, and I'll see you next week.